So basically, we look at this and see methane. When you look at that, this should be electron rich. Oxygen, we know, is an oxidizer. It goes to CO2 and water. This is just a combustion reaction, just combustion of methane. Now here, this is a bit more tricky. What's the oxidizing agent? What's the reducing agent? Methane plus CO2. This one's a bit more tricky because methane is the... Can methane ever be an oxidizing agent? I had talked about this a long time ago, but must have forgotten. Because methane can never be an oxidizer. Does anybody remember why?
Electron rich.
Not because it's electron rich. There are electron rich things that can be an oxidizer as well. Methane cannot be an oxidizer. Why?
When
it's an oxidizer, it doesn't lose, it gains. And we talked about this.
Is it Lewis acid base?
No, it's not Lewis acid base. It's a redox reaction. In this, what's the oxidation state of methane? What are the oxidation states in methane? What's special about -4 for carbon? Take a look at the periodic table. This is what we talked about. So this will be. But people say I need to repeat things at least 3 times. So I think this will be 2, number 2. The reason why carbon is special is because it's -4. When you look at the periodic table, -4, having 4 extra electrons means it's got full octet. So that means if it gains a 5th electron, where does it go?
It can't.
It goes, yeah, it's already filled its shell. It's got to go into the next higher energy shell. Is that favorable? No. And so this is why it cannot be an oxidizing agent. Just like CO2 cannot be a reducing agent. Jake, you have the answer to this. Why can't CO2 be a reducing agent? Why can't it lose any more electrons? It could potentially because what's the oxidation state of carbon and CO2? Plus 4. Look at the periodic table. What do you see about +4?
It has no electrons.
No more valence electrons. No more valence electrons. So if it loses an electron, it has to be a core electron. Core electrons cost about 10 times more energy to oxidize, so it's unlikely. And so CO2, this can only go one way, methane being the reducing agent, CO2 being the oxidizing agent. Is this reaction favorable? Is CO2 a good oxidizer? No. And so you look at a reaction like this, it looks strange. This is a very strange reaction, right? Methane being combusted by CO2 doesn't make any sense at all. You'd expect NR. But take a look at the product. These types of reactions, is it easy to predict? Well, in a way it's easy to predict because methane can only do one thing and CO2 can only do one thing. And then you got to form some reasonable products. But, in this case we're going to form carbon monoxide and hydrogen. Does that seem like an easy thing to predict? And under what conditions yields this? Well, actually, what typically happens is this. Even though the reaction's written this way, and you see a lot of these, right? And these are weird-looking reactions. Usually, what happened was somebody did the reverse reaction. Somebody did the reverse reaction. In this case, maybe it's more likely because if we think methane versus hydrogen, well, which one's a better reducing agent? Actually, that's tough because both are quite explosive, right? But then, you think about just, which one, would you think they're the same? No, you would use personal experience. And when I say personal experience, it's like this. Somebody asked me about fluorine versus CO2. How do you know which one's a stronger oxidizer? Well, it's obvious. Which one, did I already say this? Which one would you rather take a full breath of? CO2 or fluorine gas? then that tells you which one's more reactive, because I hope you'd say CO2 because we're exhaling it all the time and it's not going to cause any damage, right? But if you inhale a mouthful of fluorine, you're going to be in a lot of pain, right? Seriously. And then the other thing is, when we're thinking about reducing agents, what would you rather fill the room with? Methane gas or hydrogen gas? So we have methane gas here, right? And I got a cylinder of hydrogen. Which one? Which one? I mean, both are going to cause some serious problems, but actually neither, right? Neither. But which one do you think is more explosive in terms of? Maybe hydrogen, But, methane and hydrogen is tricky because they probably don't have as much experience with hydrogen. And so where do we rank it in terms, which way is the driving force? If we look at the two reducing agents, methane and hydrogen, carbon monoxide can go either way. Do you know carbon monoxide can go either way? Carbon monoxide can go either way because carbon is +2, which means it can lose or it can gain. And so carbon monoxide can be a reducer or an oxidizer. Hydrogen is the same thing. Unusually, hydrogen can go either way too. It could lose or it could gain to form hydrides. If hydrogen oxidizes something, it's got to be something easy to oxidize. So typically we form like alkali metal hydrides. Alkali metals can lose electrons without too much difficulty. But, so a lot of these reactions is more favorable in the reverse direction, but, it doesn't matter because we can flip it around. When we flip it around in these things, we just change the sign. If I reverse this reaction, we change the sign, delta H. And so a lot of these we look in two ways, even though one way might be favorable, the other way might not be. When we look at this, we look at a delta H of positive. A positive means what? Endo or exo? Endo. In typically endothermic reactions, you're going up in total energy, right? If you're going up in total energy, is that favorable typically, or no? That's typically unfavorable. So it looks like the reverse reaction is much more favorable. But that's not to say endothermic reactions don't occur. Endothermic reactions where the energy actually increases, do occur in chemistry. We'll talk more about those in Chem 1B, but it looks like, the reverse. Same thing with this. Take a look at this. What's the oxidizing agent here? Water. Are you gonna oxidize? If I bubbled methane gas and water, do I have to watch out? Really? Is that a frightening reaction? What would your guess be? Bubbling methane and water? Nothing. Probably nothing is going to happen. Methane is going to bubble in water. Methane is not very soluble in water. It's just going to bubble out. And so it's more likely this reaction happened in the reverse, and then they just want to put methane here. These are three things that methane is reacting with. But in this case, wait, isn't this the same reaction as above here? Isn't that the same, these two? Look at hydrogen and carbon monoxide, hydrogen and carbon monoxide. If I mix hydrogen and carbon monoxide, shouldn't I get the same product? Depends on the conditions. And so I've been having this ongoing thing about, memorization. Remember from the first test? Memorization versus theory. What I meant by memorization is people who memorize things, they just have a lot of facts, factual database from doing and seeing a lot of different reactions, right? Okay, without this, let you predict what's going to form, going backwards. This is why we have skeleton redox. Skeleton redox tells you the products, right? The product. Because it's too difficult to, why? To predict under certain conditions. You change the pressure a little bit, changes what you form. You change the temperature, it changes what you form. And so there are a lot of people trying to, map out the space, temperature, pressure, space, to see what forms under what conditions, And so a lot of these aren't so easy to predict. I mean, yes, we can't make ridiculous compounds, like, for example, CO5-. Do you think that's going to form? No, but sometimes it's hard to predict exactly what forms in a lot of these redox reactions. They can get more complex. And so all we're doing is we're starting to familiarize ourselves with redox by using the chart. And the chart is just, you know what the chart, where did the chart come from? Did that come from theory? No, that just came from experiment, like experiment 18. You guys built your own chart, right? That's how that happens. But, it's not to say everything on the chart is memorization, because then you start to see patterns in the chart, like fluorine's a better oxidizer than chlorine, chlorine's a better oxidizer than bromine, bromine's a better oxidizer than iodine. You start to see those patterns, and then you start thinking, okay, why do you see that pattern? And then you think about atomic size. Fluorine's a lot smaller. It's more aggressive at pulling electrons, and chlorine's a lot bigger. Right? And bromine's even bigger. And so something small and aggressive like chlorine can do it. And that helps you do less memorization. But still, the foundation of a chart like that is based on factual. And so the same thing here, we see these reactions, we try to understand them, see some patterns, and maybe we can make some predictions based on those patterns. If the theory were developed, the theory of chemistry is pretty well developed. If we could do the calculations, with that, then perhaps we could calculate, under what conditions. But, it gets very complicated. Well, anyway, this is it. We're going to use this to do this. And so here we have a different reaction. Here, we're going to combust methane in a very strange way to form carbon monoxide and hydrogen. Do you think this is all that favorable? Well, it depends. What do you think is a better oxidizer, oxygen or carbon monoxide? Oxygen should be better. But then hydrogen, hydrogen versus methane. Well, if it goes one way, then we'll see. But, normally when we do this, we don't form hydrogen. When we combust it, or actually we can't combust this because the hydrogen will burn too. If we were to do this reaction and oxidize the methane to carbon monoxide, we wouldn't think we'd form hydrogen, we'd think we'd form water. Right? And so another kind of weird reaction here. But anyway, these reactions you look at and then try to understand to build up your some factual knowledge. Just saying that, predicting these redox can be difficult, and the best thing to do is mix it and see what happens and balance it using skeleton. Oh, anyway, this is just adding up these reactions, and then any problems with this? You're okay? What did you guys get for your delta H?
Negative 35.8.
Negative 35.8 kilojoules. Okay, so it's exothermic. Negative 35.8. Anybody else? So you just rearrange these until you can get them to add up, and that's the basic foundation for a Hess's law problem. Most of them are just time-consuming, not terribly difficult, just time-consuming. Okay. I'll look at the examples in the book and work on it. Let's finish the problem we were looking at the other day. In the problem we were looking at the other day, we did something much easier than using Hess's law like this. This is Hess's law using any old equation and then just reversing and multiplying. If you multiply an equation by n, let's say n times reaction 1, what do you do to delta H? Let's say I multiply 1/2 times reaction 1. If I have half as much reaction, I'm going to expect half as much delta H, half as much energy. And so it would just be n times delta H. And so we have all those tools for this, but the easiest application of Hess's law is using Hess's law from delta H's formation, which we talked about, right? And so did we finish calculating the delta H for glucose, the delta H of combustion of glucose? No? All right, let's complete that. We had it written on the board, right? All the numbers? All right, and so we use the delta H as a formation, which is easier than what the problem I just showed you. The reason it's easier is because we're only using one type of reaction. That one type of reaction is called a formation reaction. What's the definition of a formation reaction? It's a formation of do you have it in your notes? 1 mole from the standard. Okay, what is this? You know, look back at the previous reactions. The previous reactions had a delta H naught. What does that little superscript 0 mean? Standard thermodynamic conditions. And so the previous set of reactions we looked at, what do we know about those? Under what conditions were those? Okay, we had 1 ATM or 1 bar, 1 molar solutions. What about the temperature of that last set?
There is no standard temperature.
There is no standard temperature. Do you think the temperature in the last set, could it have been at 298? Could it have been at 298? No. The last set of reactions must have had it at, probably at, greater than 373 Kelvin. How do I know? No, not because we were burning. This is, you know, when we're talking about state functions, all I care about is the starting temperature and the ending temperature. Could be combustion. Doesn't matter how hot the temperature gets during the reaction. What matters is my initial temperature and so my initial and final temperature in those reactions must have been greater than or equal to or greater than 373 Kelvin. Why?
Because water is a gas.
Because water is a gas. That's how I know. But do they tell us what the temperature is? No, they don't. And so we have to make an assumption. What assumption did I make? Or what assumption do you have to make to solve the last problem? Well, that the temperature for reactions 1, 2, and 3 are the same. If they aren't at the same temperature, we can't add those because they're at different temperatures, right? And delta H depends on the temperature. So, anyway, we have this. Did I talk about? Oh, Andrew, you were asking about the beginning part of the video. What was I talking about at the beginning part?
Talk about like the Q, does QB change, does QB
Oh, Q, okay, I'll talk about that too. Well, what do we know about this? Well, we know that this delta H naught, this means 1 ATM or 1 bar. And then we use these, you know, the sum of the delta H's of formation. What does this F mean? The F means just what we were talking about earlier. All right. It turns out appendix D is under bars or atmospheres? Bars. So appendix D is 1 bar. Is that all we know about the appendix D data? And appendix D is 1 bar and room temp, 298 Kelvin. And so that means this is going to be fixed. This delta H of the reaction has to have a beginning temperature of 298 Kelvin and a ending temperature of 298 Kelvin. That's it. It's fixed. What if we want it at a different temperature? We can't. In Chem 1B, you'll be able to figure it out. In Chem 1B, we'll be able to figure out what happens a little bit with temperature and try to figure out what to do with that. So it turns out delta H, it doesn't really change that much. all that much with temperature.
So when do we care about temperature and when?
We always care about temperature. We're always cataloging the temperature in the back of your mind. When you do these calculations, you have to worry about what is the temperature. In Chem 1A, no. In Chem 1B, yes. But you might as well get in the habit now so that it'll make Chem 1B easier. We think about the temperature. A lot of the problems in Chem 1A here, they don't specify the temperature. It might be 290, it might be something else. But the reason is because it happens all the time in Chem 1B that somebody uses a value at 298 for a value that's supposed to be at 1500 Kelvin. You can't do that. At 1500 Kelvin, it's going to be different. And so that's the issue. And so this boils down to what you were asking about, Q and all this other stuff, delta H, delta U. We'll talk a little bit about that some, but if the beginning part got chopped, it's because I forgot to start the recording. But I'll talk about it a little bit. All right, so did somebody finish this calculation?
Minus 2802.5 kilojoules.
Okay, minus 2802.5 kilojoules. All right, now that we have this, what this means is it's for the reaction as written. What the reaction as written, what does that mean? This heat is for the reaction as written. Well, the reaction as written had 1 mole of glucose, 6 moles of O2 gas. Which yields the CO2 and the water, 6 and 6 each of those. And so if I do the reaction as written, 1 mole plus 6 moles yields 6 moles plus 6 moles, then I'm going to get 2802.5 kilojoules of energy released.
I don't think so. You got numbers wrong.
Oh, the number's wrong?
I think so.
What did you get?
3,634.
3,634?
Well, that's the number we wrote down on the phone.
I know, it's written like that.
3,634 seems high, actually. Seems a little bit high. Let me, anybody else do this?
We got that number when we calculated it.
You got that? Okay. Yeah, 3,000. I know the delta H of combustion of glucose. Actually, this is it here. I know. And so, since I'm kind of rushed for time, I'm going to skip going through it again, the calculation. But this is the correct number, the combustion of glucose. And so, normally we write it like this. Delta H is in kilojoules or kilojoules per mole. And so typically we write 2802.5 kilojoules. This is our delta H naught. Or we write this as minus 2802.5 kilojoules per mole of glucose. Or we write this as minus 2802.5 kilojoules per 6 moles of O2, etc. And so these are our energy conversion factors. So if I knew, let's say I knew 12 moles of O2 completely reacted, how much energy? Well, 12 moles of O2 completely reacted, it's got to be double this amount here in terms of energy. Or if I knew 3 moles, if I knew 3 moles of CO2 were produced, then how much energy? Well, it's got to be half this amount, right? And so this is the way I use this stuff. Sorry. Let me do that. So now, how do I use this in a particular problem? Well, I just got to figure out how much reaction I have, and then I can do it. Well, this problem is going to approach it from a different perspective. This problem is going to say, I need a certain amount of energy. If I need a certain amount of energy, then how much glucose do I have to burn? And so this is it, the problem. The metabolism of glucose yields CO2 and water as products. And so I asked you, this is burning, this is combustion. If we metabolize it, metabolizing it doesn't occur in one step, right? It occurs in a whole bunch of steps in the body. But if you think about metabolizing glucose, the products are exactly the same. If we were to eat glucose and inhale O2, we're going to exhale carbon dioxide and produce water in the process, liquid water. And so this is a state function. And so if the starting and the final are exactly the same, then the energy will be exactly the same, no matter how you do it, right? It doesn't care about the path. The starting and the final points are the same, so it's always going to be the same amount of energy. That's why we like state functions. Right? State functions are always the same. And so this is how some people, this is how they used to do food calories in the old days. In the old days, they did food calories by burning. You got some food, you burn it and see how many calories are released, right? Completely lost it. But, you know, that's not accurate because, you know, for things like the sugars, which are carbohydrates, and fats, this is no problem. But for proteins, you know, you form different compounds. Normally when you burn, proteins contain nitrogen also. When you burn nitrogen, you usually form NOx. But in your body, you don't necessarily form NOx. You form other things as well. And so they're being more. And then there's things like insoluble fiber. If you burn insoluble fiber, you know, you'll form CO2 and water and energy. But does your body actually metabolize insoluble fiber? Like wood chips? No. And so there are more accurate ways of doing food calories now than that. Okay. But anyway, getting back to this, heat released in the process, okay, this heat, when we do this, what can we do with this energy? Well, you know, remember this is equal to, delta H naught is equal to Q. No, well, delta H is not, delta H is equal to Q sub P. Well, delta H is equal to Q sub P, so does that mean when I metabolize the glucose in my body, all that I can use this energy for is making heat? I can't do any work, right, muscles, because it's just Q. What happened to W? Well, W was, you know, the expansion and contraction of the gases, right? In this case, is there much work? What did we say about the work last time? In fact, I'm maybe spending too much time on this particular problem. What did we say about the work?
Negligible.
Negligible. Why?
You're going to recite it.
Yeah, the volumes are going to be pretty much the same. Right? The solid and liquid volumes aren't that different. And so I do this reaction, I get this heat, and so is the only thing that's going to happen is it's just going to warm my body up and maintain body temperature. I can't do any work because delta H is equal to Q. So think about when you burn coal. If you were to burn coal, that produces a lot of heat. Can you do work? Because it's just making heat, right?
couldn't work by converting like heat to some other.
Right, so what we do is like burning coal, you would take that heat and then convert it into steam, and then you could drive like a steam locomotive, right, engine or something. And so what you can do is you can take this energy, which came off as heat, and then convert it into work. That's one way. And so you take heat and then convert it into work. Is that very efficient? Yeah. But there's actually another way. Another way you can do that is you don't make the heat in the first place, right? What you do is, let's say your body goes through this process here, and then it converts what we have chemical potential energy into work. And so this is like this. Remember, do you remember if I should the slide like this, right? Somebody slides down the slide and then generates heat like this. Somebody slides down the slide and generates heat, and then what we're going to do is we're going to capture that heat here, warm up some water, and hopefully boil some water to make some steam to drive a piston, and get some work out of that. Is that very efficient? No. And so what I can do is I can try to convert the chemical potential energy directly into work, right? Instead of going to heat and then converting the heat in, actually, the reason I'm talking about this is because of the people who have physics, and they talk about the Carnot cycle. Have you guys heard of that? About converting heat into work. And so some people in chemistry, they get it confused because we don't convert heat into work necessarily. We convert chemical potential energy into work. And so I had this long debate with one of my students who said, I've tried to figure out a way to convince them to understand that, it's not taking the heat off the slide and then making this into work. It's here, if we have a pulley, we aren't going to generate as much heat, we're going to convert it into work. And so even though this says heat, we can convert the chemical potential energy, because delta H, remember, is the U and the work, right? We can convert that potential energy into work. And this is what your body does. It doesn't, and so what it does with this is it converts it into high energy molecules, and that's work. Well, anyway, it doesn't happen with this. Let's say heat released in this process is converted to useful work with about 70% efficiency. 70% efficiency means you take all this heat, and 70% of this heat can be converted into work. The other 30% will be lost as just normal heat. Calculate the mass of glucose metabolized by a 58.0 kilogram person in climbing a mountain with an elevation gain of 1,450 meters. Assume that the work performed in the climb is about 4 times that required to simply lift a 58.0 kilogram mass by 1,450 meters. And so here's a 58.0 kilogram person, and they're going to climb a 1,450 meter peak. How much energy does that cost? Well, it turns out just to pull this, let's say you hook this person up on a pulley and then just lifted them straight up, and this was a frictionless pulley, and there was no heat generated, and then how much energy would that have cost? And so this is from physics, and you don't have to know this at all, but from physics, we're looking at the energy is going to equal the mass times g, which is gravity times the height, mgh. And so this is the amount of energy required to pull this up. from physics. And so we think, well, we aren't going to hook up a rope and have a frictionless pulley, so what we're going to do is we're going to estimate it. It's going to cost at least 4 times this. You know, 4 times as much as the minimum. This is the absolute minimum amount of energy required. 4 times the minimum. Okay, and so let's go ahead and calculate the amount of energy required to climb that mountain. So that's 4 times the mass is 58.0 kilograms times g, which is 9.8 meters per second squared, times h, which is 1,450 meters. And this is going to give us
3296,720.
3296,720 joules. Kilogram meters squared per second squared. It's joules. So, 300, what is this? 3,296,720 joules would be 3,296.72 kilojoules. This is more sig figs than we're allowed because do you think it's that precise? How much energy? And so it's just about 3,300 kilojoules, we'll just say. But we'll leave it like that because they said 4 times. And so I need that many kilojoules. All those kilojoules are going to come from glucose with 70% efficiency, right? That we're going to convert. And so this is the way we'll do it. We're going to just use dimensional analysis. That is 3,296.7. This is more sig figs than I'm allowed. Kilojoules required. This is the kilojoules produced from the reaction. And so what do I do about the 70% efficiency? Well, the 70% efficiency says that I'm going to get 70 kilojoules for every 100 kilojoules from the reaction. So 70 kilojoules of work, right, for every 100 kilojoules of energy produced from the reaction. Or in other words, 70 kilojoules, what should I say? How do you want to label this?
70 useful.
Yeah, for every 100 kilojoules. Okay. Usable for every 100 kilojoules total. Produced. And then I'm going to use this conversion factor here. Now, should I have a negative here or what? No, because what I'm going to do is I'm just going to convert it into a word rather than a sign type thing. So I'll just say 2802.5 kilojoules released total per 1 mole of glucose. Yeah, then we convert it into grams. Yeah, so did I write the molar mass of glucose last time? 180.15? What was it? Maybe I didn't. 6 times 1201 plus 1212 plus 6 times 16. 180.15? 180.18?
Yeah.
180.18 grams of glucose
Per mole.
per mole of glucose. And so this gives us how many grams of glucose?
302, 46,000. 7737.
Okay, that's probably, so about 303 grams of glucose.
Yeah.
Glucose required. Okay, so you can double check that calculation. All right, so that's some applications. Now, conceptually, you know, the calculations are not difficult. A lot of the calculations in this chapter, but the concepts are difficult, especially when it comes to things like heat and work, because here we're calculating heat of reaction, but you know, how's that heat of reaction being converted into work? Well, that's what your body does. Converts it into work of making energy molecules that are used for muscles. But let's talk about the question that was on the piazza there. Q. You know, this whole thing is very difficult to keep track of, too. And it depends on how you define it. And so, if, so maybe we should do more of these. Let's revisit number 63. How about that? Only one of the following expressions holds true for the heat of a chemical reaction, regardless of how the reaction is carried out. Which is the correct expression? And so QV, regardless of how the reaction is carried out, QV holds true. Yes or no? What do you say? And if you say no, why? Okay, regardless of how the reaction is carried out, QV holds true.
No, it's not.
Yes or no?
Yes.
Okay. B, QP. This is A. B, QP. C, delta U. D, delta H. Is that it? Yeah. They're saying only one of these holds true. If it's only one, then you would automatically say which one. If they're saying only one. Delta U. You automatically pick that, right? But this is unusual. This problem is very weird because why isn't QV? What is QV anyway? Constant volume. What is? If you look at the heat at constant volume, delta U is equal to Q plus W. There's no work done. So QV is equal to delta U. So shouldn't it be?
Well, but the question says regardless of how it's done.
Regardless of how it's done, well, QV.
Doesn't it change in the constant pressure and constant volume?
QV, doesn't it change at constant? Yeah, it does. You're absolutely right. It changes depending on if you do it at constant pressure or constant volume, but QV is kind of stuck. We're stuck, aren't we? Well, delta U, we can change the what? Temperature? Delta U, we could change the temperature too. So is delta U at 298 Kelvin the same as delta U at 2000 Kelvin?
No.
Yes.
Maybe, maybe not. How can we know? Is it always the same? Delta U at 4 Kelvin the same as delta U at 1,000,000 Kelvin? What do you think?
Depending on how the reaction is.
No, you know, those things, well, you know, there are factors there. We'll look at the factors in more detail, probably in Chem 1B. or you will, when you take Chem 1B, look at it in more detail. But, there are changes in potential energy depending on what, the kinetic, delta U is going to have the same initial and the same final. So the kinetic energy doesn't change. But the potential energy could change depending on the temperature. Right? And so, is it frozen? Is it a gas? Those things change, right? And so the potential energy can change as well. And so, this problem, maybe I should qualify this problem. We're going to stick with something and we aren't going to get confused, so it depends. QV, does it change regardless of how you do it? Well, one, that's a very tricky question because we can't do this any way we want. The only way we can do this is at constant volume, so does it change? No. And so this is why I was trying to say something. As far as thinking goes and keeping your thinking straight, QV, we're stuck. QV is going to be QV. QV is like the 65 mile an hour speed limit. It's stuck. You can't do it. You can't do this. I want to drive the speed limit. I'm going to drive 75 instead of 65. Can I do it? If I want to drive the speed limit. No. If I want to do QV, then I'm stuck. I got to do 65, right? Of course I can go 75, but I got to drive 65 because it's restricted. And so QV is restricted. We can't do this any way we want, right? We can't. Now, there's another thing that people will go. QV, remember this? This is only if QV is per reaction as written. Otherwise, if you don't know what the reaction as written is, then QV is equal to the amount times delta U, right? Because we have two things we have to juggle with. One is sometimes you don't want to burn a full mole, right? Sometimes we want to burn 1/10 of a mole. If we burn 1/10 of a mole, then we're going to get 1/10 the amount of heat, right? Or sometimes I want to burn 10 times the amount shown. If I burn 10 times, I'm going to get 10 times the heat. And so does that mean Q is changeable because the amount changes? Yes. And so this is why they're saying this is variable. It's not variable because it's variable because the amount can change. But it depends on if you're looking at this. When we're looking at this, QV is delta U, but this QV is for the reaction as written. This QV is just for any old amount. We don't have to do it. It's like, if you burn 1 mole of glucose, are you going to make it to the top of that mountain? No, you're going to need at least 2 moles. More than 2 moles, is it? No, less than 2 moles. 360, you said 303. Less than 2 moles of glucose, right? And so the reason they're saying that QV is kind of fixed, right? But the reason they're saying it is because I think the amount, if we burn less or more, we're going to get more or less heat. Does that make sense? And so this is the reason they're saying it's variable. But the reason I'm saying it's fixed is it's always going to be the same amount of heat per gram. Does that ever change? No, if I burn a gram of glucose, I'm going to get the same amount of heat. If I burn a mole of glucose, I'm going to get the same amount of heat. So to me, to my thinking, it's fixed. Right? It doesn't change. Of course we can burn any amount we want, right? But to the book is thinking, well, it changes because you can burn 1 gram, 10 grams, 15 grams, right? And so it's very trick, this question. If you get a question that you think that I wrote is trick, then define it, define it. This is my thinking on this question. And based on my thinking, I'm considering QV doesn't change. It's always the same per gram or per mole. And you can only do it under constant volume conditions. And so that's why I circled this. This is true. Regardless of conditions, you're always going to get the same amount of heat per gram or the same amount of heat per mole. But the amount of heat, of course, you can burn different amounts, therefore the amount of heat can be variable. The reason I'm doing it this way is because this is very different than QP. QP and QV are different in this sense. Because QP is definitely different, and your book is saying it's the same in that this is false, right? QP is saying what? Am I always going to get the same amount of heat? No, because it depends on how much work. When you look at the glucose, if I burn the glucose in a bomb or out in the open lab, I'm going to get 2,802 kilojoules per mole of glucose I burn. But when that's of heat, just pure heat that I can use to warm something up. If I eat that mole of glucose, am I going to get 2,802 kilojoules per mole of heat? No, hopefully I don't get all that because I need to do work. And so this is totally different. This depends on how much work is done. So even though I got that delta H here, I could have variable amounts of work done using that energy, right? And so, because we only factored in one type of work. When we start factoring in the other types of work, then that can change the amount of delta H I get because I got to add more work terms. Remember, delta H is equal to delta U minus W. And we only factored in one, but if there are more than one, then we got a W1 plus W2 plus W3, right? And it's going to change the amount of heat I get. In other words, heat. And so this is false. Regardless of how I do it, it's not always the same. Okay? How about delta U?
Regardless of reaction.
Yeah, actually this one doesn't depend because it doesn't, I could have thousands of different kinds of work, but my delta U will always be the same. And so delta U, this is true, right? Now here comes another tricky thing. The delta H, what did I say, true or false? Regardless, it's always the same. I said true. Your book says false. Why does your book say false?
Because we don't look at it as a state function.
Delta H, the reason I say that this is true, regardless of how you do it, is because delta H automatically means you're locked. You're constricted to do it a certain way. What is the certain way you have to do the reaction? Constant pressure. If you aren't at constant pressure, then delta H is false, right? But delta H is, delta H is delta H. The speed limit is 65. If you're stuck in traffic and only driving 5 miles an hour, it doesn't matter. Did that change the speed limit? Excuse me, did that change the speed limit? No, the speed limit's still 65 even though you're putting along at 5 miles an hour, right? And so to me, this is a state function. This is why it's always true because, yeah, we might not get this amount of heat. We might not do it at the speed limit, but the speed limit's the speed limit. The speed limit's already been fixed. This has already been fixed. This is why they compile these things in Appendix D. If they compile these things in Appendix D and they're changing all over the place, then why do we have 5 pages worth of delta H's in here? If they're variable. Well, this is why I said this is true because we got to restrict it. What were the restrictions? 1 bar, and for Appendix D, 298 Kelvin. If we're at 1 bar and 298 Kelvin, it's always the same. Now, if I bring this up to 2,000 Kelvin, then forget it. We don't know, right? But the same thing goes for delta U. If I brought this up to 2,000 Kelvin, do we know? No. And so do you understand what I'm saying? This is why this chapter takes I'm spending too much time on this chapter, but I gotta spend too much time on this chapter because there's certain concepts that are very confusing reading in the book and then listening to me because I'm conflicting with the book sometimes, right?
So how's the test going to be like?
All right, well, some people say, I don't, the stuff on the notes, I can't follow it. I just know the book. Well, if you know the book and you're consistent with the book, and I look, you're being consistent with the book, then you're okay. I'll still give you. And so, on the test, but you got to be consistent with the book. Like one problem you can't be consistent with the book, and the next problem you're consistent with me. You're going to stick with something and stick with it. Okay, so if you like to call this, which one's bigger, plus $10 or minus $10, and if you say they're the same, then you're consistent with me. If you say plus $10 is bigger, then you're consistent with the book. Just make sure you're consistent with the book throughout. Then I'll give you points. Otherwise, stick with me. Does that make sense? And so, just be consistent. Either you learn it like Petrucci has it, or you learn it what I was just telling you regarding this. Okay. And so number 63 is confusing because I conflict with that. But do you see why I'm conflicting with it? Okay. Why are they saying this is false? Why did they say this is false? It changes regardless. Because, you could do delta U at a different temperature.
Because they don't restrict the work.
Maybe they're not restricting the work to P delta V, but by the very definition of delta H, the work has to be restricted to P delta V. And no other work is allowed when you have delta H. So I don't understand it exactly. It should be fixed. If somebody burns 1 mole of methane here under this pressure, 1 atmosphere, under 298 Kelvin starting and final, then they should get the same amount of heat as somebody in San Diego doing the exact same thing under the exact same conditions. Don't you agree?
Yeah.
And can we do it under a different condition? No, you can't do it under a different condition because each delta H you have to specify the pressure and the temperature. All right. Do you want to do more delta H and delta U's? Yeah.
It is the end of chapter 7, or?
This is the end of chapter 7. I'm not going to talk more about, are there questions about chapter 7 homework or anything? What's that?
We're doing the full chapter 7 homework, right?
Yes.
Yes. Whole chapter.
What's that? Well, we'll see what the next test comes out to because I need to cover chapter 8. So take a look at these problems, the homework problems, and then we'll talk more about them. But just work through the homework.
How many chapters will you cover for test 3?
Well, we'll see. Let me talk. I'm going to go. Chapter 7's tricky because of all these definition things, but chapter 8 is a lot more straightforward. And so I'm going to zip through chapter 8,
Well, we have the problem you gave us at the beginning of class. Was that supposed to be done using the chart in the back of the book?
No. That's just done manipulating the equation and getting them to add up.
Can you show us like guideline how to change the numbers, X by 3 or something?
Which one? For that?
I couldn't get to the final answer.
You couldn't get the first problem?
Yeah, different.
I don't know
You got
if
different
numbers
answers?
changing reversing.
All right. We'll do this on the board. There's a strategy that you use when you do these. So this is our goal equation, CH4. All these are gases, so I'm going to leave off gas. 1/2 oxygen. If they weren't all gases, then I would put the state. This is what we want. And so, in other words, I gotta look, I want 1 mole of CH4 on the left side. Which equation has 1 mole of CH4 on the left side? All of them. If all of them, then I could use any of the 3. So I'll skip that. Then I want 2 moles of O2, or not 2 moles, 1/2 a mole of O2. Which one has 1/2 a mole of O2 on the left side? None of them. Which one has O2 on the left side? The first one. And so what I'm going to do is the first one has 2 O2s. I'm going to multiply it by 1/4 to cut it down to 1/2. And so what I'm going to get is 1/4 CH4 plus 1/2 O2 yields 1/4 CO2 plus 1/2 H2O. Good, now I got this. That's what I want. I want 1/2 O2 because that's my goal. Okay, the next thing I want is 1 mole of carbon monoxide. Which one has 1 mole of carbon monoxide on the right side? Number 2 and number 3. Since I have a choice, I'm going to skip it. Why am I going to skip it? Because I have flexibility there. Then I want 2 moles of hydrogen on the right side. Which one has hydrogen on the right side? 2 and 3. And so now I have some choices to make. All right. I can either start off with the carbon monoxide or the hydrogen. Which one do you want to do? You know, I want 1 mole of carbon monoxide. Reaction 3 already has 1 mole of carbon monoxide. I'm just going to use that as is. Right? When I change this one, I have to do something. This is going to be 1/4 times delta H1, 2, or 3. Delta H1. 1/4 delta H1. Okay, then I'm going to use reaction 3 as is because that has 1 mole of carbon monoxide already. So this is going to be CH4 plus H2O yields CO plus 3H2. And since I use that as is, it's just delta H3. Okay, so let's see what I have so far. I've got my oxygen, I got my carbon monoxide, but I have too much hydrogen, look, right? And then too much methane, and I got this water, I got to get rid of this water. And so how can I get rid of the hydrogen? The only way I can get rid of the excess hydrogen is to, I have to use reaction 2 or 3. If I use reaction 3, it won't work because I just used reaction 3. And so I have to use reaction 2 to get rid of the extra hydrogen. Do you know how I do that? I flip around reaction 2. And then I multiply it by, so how many hydrogens do I need to get rid of? 1 mole. I have 2 moles of hydrogen, so I'm going to multiply by 1/2. And so I'm going to reverse reaction 2 and multiply by 1/2. So when I reverse reaction 2, I have to change the sign. So now it's going to be a negative. In other words, change the sign of delta H2 because I went backwards, right? State function. So rather than going up, we're going down, you know, or whatever. And then I multiplied by 1/2. And so it'll be negative 1/2 delta H2. Okay, now look at this hydrogen cancels out 1 mole of these and leaves me with 2 moles. And so now I have my 2 moles of hydrogen, that's good. But what about all this other junk? Well, assuming I did it right, all the other junk hopefully cancels out. And so I don't worry about all the other stuff until the end. But you know what? Did I just do the wrong equation? No, I didn't. And so let's take a look at what I got now. I have 1/2 methane. That's going to make this 1/2. And then, you know what? I just screwed up my carbon monoxide. My carbon monoxide just canceled out my carbon monoxide. I didn't want that to happen. And then my water, here, I have 1/2 water. And now I got 3/4 CO2. So this looks like it's turning into a mess. And so, what should I do now?
You should just,
No, don't give up. All we do is, all we do is,
You multiply equation number 3.
we need to get rid of some CO2s. So how can we get rid of some of the CO2?
you get rid of water first.
All right, we can get rid of
So the
water.
first equation multiply twice of the third equation.
Who got the answer the first time?
I did the first and the third one,
Mhm.
and then I multiplied the second one by 2.
Okay.
And then from there, I used the middle equation, and I got it.
Okay, well, that's good. You went down the wrong path. Maybe I'm going down the wrong path, the long, windy path, and you have the more direct path. But you know what? I don't think we should give up on this path. even though this path might be the longer, you know, sometimes you hit that sequence and it just works out perfectly, but in this case it didn't. And so we got to keep going. So keeping going, we either get rid of the water or we get rid of the CO2. And so which one do you want to get rid of? The water, you said, right? But we have two choices for getting rid of the water. We can either use reaction 1 or we could use reaction 3 for getting rid of the water. Reaction 1 or reaction 3? Okay, if we use reaction 3, that's good because that gets us carbon monoxide back. But maybe we're just going in a circle. And so let's go ahead and use reaction 3 to get rid of the water. Or do we? We'll see. And so if we use reaction 3 to get rid of the water, then what do we have? We are lost. We are lost. But this is the problem. This is the situation of doing Hess's law. Hess's law, I told you, these are not difficult. These are just time-consuming. You know, if this doesn't work, then you backtrack and you start, okay, we had some choices that we made here, right? You backtrack and start from another choice. But the thing is, you know, like I said, don't give up on this because it'll be the same thing starting over again. We just add more reactions until it cancels out. And so normally what you do is you look, rather than focusing on getting rid, we focus on getting. And so here, we lost our carbon monoxide. Let's get the carbon monoxide back here. Right? And so what one would yield the carbon monoxide? We need 1 mole of carbon monoxide here, and I accidentally canceled it out here. I shouldn't have used this one here, because that got rid of the carbon monoxide here. Right? And so how can I get the carbon monoxide back? Well, I have two choices. I could use reaction 2 or I could use reaction 3. In this case, I used reaction 2. Remember that?
No, we used 3.
Is this 3? Oh, yeah. But, you know, in this case, I used reaction 2, but maybe I should have tried reaction 3. I mean 3. In this case, we use reaction 3, but maybe I should have tried reaction 2. And so trying reaction 2, I'm going to have to multiply by 1/2. So I get 1/2 CH4 plus 1/2 CO2 yields CO plus H2. This is delta H2. You know, there's nothing, you know, there's absolutely nothing wrong with getting lost and getting mixed up. This is perfectly normal. I mean, everybody does this. Even who you think are the experts. The masters, yeah, sure, they've done them so many times they could mentally pick it out, right? But, you give them a new problem, it's the same thing. You start trying to look and see what works and what doesn't work. It's no big deal. Okay? And so here we try this and then see. Okay, now I have my 1 mole of carbon monoxide, right? But I'm lacking in the H2, so I need 1 more H2. But I'm not going to use reaction 2 to do it. I'm going to use reaction 3 to do it and see where I end up. Okay? And then try it. But we're out of time now. Continue. We're going to start chapter 8, though.